Okay, today we're going to spend a little more time on solving differential equations. Last time, if you remember, we solved differential equations that had only x's on the right side, if you will, and that made the solving part fairly simplistic in terms of the fact that when we had a y over here, y dy, or just a 1 dy, I should say, we ended up with y equals, and so the majority of the problem was already done in terms of the algebra here. So we're going to see what happens if we have something like this where we have x and y involved. And what do we do if we're going to solve this differential equation? And in review, that means to find an equation for y whose derivative is this and whose initial condition is this. So it must satisfy the initial condition 1, 1, and it also has to have this as its derivative. So to do so, we're going to separate variables. And again, in this case, we have a y squared, so that y squared will have to go to the other side by division, and the dx will go to the other side to the right by multiplication. So once we have it at that point, again, it's already more complicated because in the previous problems we had just 1 dy every time, but in this case we have some expression in y. So if we anti-differentiate both sides, keeping in mind that y to the negative 2 is what we have here, we can go y to the negative 1 divided by 1, negative 1, and then on the right side we'd have x cubed over 3 plus c. And as I showed last time, we will immediately put the initial condition in at this point. If we put a 1 in here, we get 1 to the negative 1 over negative 1, and we get 1 cubed over 3 plus c. And ultimately 1 to anything is 1. And if we divide it by negative 1, we get negative 1 on this side. And over here we get a third here. And if we subtract, we get negative 4/3 over here, would be our c value. And so at this point, going back to our original, we would have the following. And that would be our equation so far. So the issue here that we didn't have last time is that at this point, the equation is not solved for y. So once we find c, plug c back in, rewrite the equation with c in there, which is negative 4/3 in our case, and then at this point we need to get that y by itself. So in this particular case, we'd multiply by negative 1, we get y to the negative 1 equals negative x cubed over 3 plus 4/3. And then from there, we could rewrite this as 1 over y. I would probably rewrite this as 4 minus x cubed all over 3. And then if we use the cross product here, we can get y by itself, get y out of the bottom, if you will. So it would be y times 4 minus x cubed, that is, not 4x. And over here, that would equal 3. And if we divided, we'd get 3 on top, 4 minus x cubed on the bottom. And so with that said, we would have our problem done. This initial value problem will be solved. We have the function whose derivative is this and who satisfies the initial condition 1, 1. Alright, now we could check that 1, 1 first fairly easily by putting a 1 in here. And if we do 3 divided by 4 minus 1 cubed, 4 minus 1 cubed of course is 3. 3 over 3 is 1. So it does in fact satisfy the initial condition. Now is there a way that we could check this to make sure that it actually satisfies the derivative part? Well, of course, we can find the derivative here. So if I wanted to check this, I'd go y prime equals, and I'd probably first rewrite this as 4 minus x cubed to the negative 1. And that way I can go negative 3, 4 minus x cubed to the negative 2 times negative 3x squared using our chain rule. And so on top we'd have 9x squared, and on the bottom we'd have 4 minus x cubed all squared. And so that would be our derivative. So the issue then is that the same as what we have here? Well, with that we can take a look and see if we can figure it out. Well, we know that this is ultimately x squared times y squared. That was our given derivative. And our question is that the same as x squared times y squared? Well, our claim was that this right here is y. And so if I did, at this point, if I did x squared times y squared, 3 minus 4 x cubed all squared, I would get x squared times 9 on top, 4 minus x cubed all squared on the bottom. And ultimately, if I put those two together, how does that compare to this? Well, of course, it's the same thing. So guaranteeing that I do have the correct answer, which is ultimately this. So again, we're setting out to find the equation whose derivative is this, and that satisfies the initial condition given. Okay. All right. So we saw also in AB that we do this separation of variables. Anytime we have a differential equation that's dy dx equals ky. And this led us to a special equation. And that special equation, if we separate the variables, we can, we'll remember it after we get through solving here. We'll say that we just don't know what the k value is here. We don't know what the initial condition is, but in general, If we separate the variables, use the same technique that we just did, and we integrate both sides, we're going to get natural log of absolute value of y over here. We're going to get kt plus c over here. Actually, I should say kx. We're using x as our independent variable, so kx plus c. And then at that point, we would compose both sides with e. That would leave us with y over here. We get e to the kx plus c up here. And when we use our rules for exponents, we could rewrite that as kx and c separate, e to the kx times e to the c, the same as e to the kx plus c. And remember that right there is just a constant, so we always wind up with something of the form e to the c times e to the kx when we put it out in front, because really e to the c is just a constant, and we wind up with that as our equation. And this should look familiar because ultimately this c is our initial value, and if we rewrite it in terms of our y sub 0, which is our initial y condition, then we get the general form of y equals y sub 0 e to the kx. So ultimately, with that said, anytime that we have this differential equation, dy dx equals ky, where ultimately this y is growing in proportion to how much, the dy dx, I should say, the rate of growth, is proportional to how much we have in terms of the y quantity, okay, we're always going to get this differential equation. And so anytime we're given something of that form, okay, we can either go through the work that it takes to get to the bottom line here, or we can just recognize that the formula for this, the y is always going to be of this form when we get done. Okay, so let's take a look at an AP problem. This is actually a 2011 AB5. Okay. And to take a look at the differential equation given here, we have dy dt, or dw dt that is, and that's equal to 1/25 times w minus 300. Okay, and the initial condition here is that w of 0 equals 1400. So we're just going to look at this from a solving standpoint. We'll deal with it a little bit more later when we're in our review part. But bottom line here is just to illustrate, when we have this differential equation here that we need to solve, we'll do the same technique in terms of separating variables. We'll get w minus 300 on this side, and we'll leave the 1/25 on this side, and we'll have that as our result. So anti-differentiating at this point, oops, I lied, we have 1 over that because we're dividing, sorry. So 1 over w over 300, and the antiderivative of that is ln of w minus 300, since that w minus 300 is linear, and over here we'd have 1/25 t plus c. Right, and at this point we would use our initial condition, so we do natural log of 1400 minus 300, 1/25 times 0 plus c, and so we'd get natural log of 1100 over on this side. 1100 equals our c. So at this point we'd move back to the natural log of w minus 300, and over here 1/25 t plus ln of 1100. And notice that we're still following exactly the same steps here. We're separating variables, integrating both sides, and then we're plugging in our initial condition as soon as we find our two antiderivatives. And in the AP test, keep in mind every part of this is worth points. This is going to be a 5-point out of 9 problem, which is pretty significant. So once we find c, plug our c back in there, and at this point we need to forget w by itself. We're trying to solve the initial value problem, which means find an equation for w in terms of t. So we'll compose both sides with e. We'll be left with w minus 300 on the left. And on this side, if we compose both sides with e, we get 1/25 t plus ln of 1100. Right. If we use our same technique that we did over on the left, we're going to get w minus 300 still. This is going to be e to the 1/25 t and e to the ln of 1100. Right. And then from there, we know that e to the ln of 1100 is just 1100 because e and ln are inverses of each other. So we get the undoing, if you will. So we get 1100 e to the 1/25 t. And the final step, of course, to get w by itself is to add 300. So our final answer for the problem would be w equals 1100 e to the 1/25 t plus 300. And that would be the solution to the differential equation. And on the AP test, this is worth 5 points. So each part, when we separate the variables, that's 1. When we find the two antiderivatives, that's another. When we add c to the end of it, we get another point. When we find c, we get another point. And then when we finally solve for w, we get the 5th point. So ultimately, this is worth 5 points on the 2011 test, which again, a 5 out of 9 is fairly significant for one problem. So very important that we're able to handle dealing with solving differential equations by using the separation of variables technique. So that's that, and your assignment for this, it will be section 7.4. You have 10 problems to do, so good luck.